As usual, after wishing you a good digestion, I briefly sum up the second lecture. This is the third one. The third lecture, for the first time, introduced definitions in the mathematical sense, in particular, event, possible world, state. Event, modulo equivalent, logical equivalent, became a member of a Boolean algebra. And in the Boolean algebra, you see the family of all events under consideration with their mutual relation. Automatically, the Boolean algebra speaks of its possible worlds. Automatically. Once you have this family of events with the operations of a Boolean algebra, you have the homomorphism of the event into the truth values. Let's say, the smallest possible Boolean algebra, two elements with the Boolean algebraic operations, which are minimum, maximum, and negation 1 minus x in the 0, 1, 2 element set. So it's a rich structure. So I said something very sophisticated after all. Although Bookie publishes events as statements or names of horses or pairs of football teams together with betting odds, events are given a probability as equivalence classes of the events, unless you want to ruin Bookie at the very beginning. Because if you give different probability to two events which are the same event, and I gave the example of in June or after May and before July, then Bookie gets ruined at the very beginning. As if he gets ruined if he gives betting odds bigger than 1 or less than 0. And when we get them, of course, who ask what are equivalence classes of events, they are elements of Boolean algebras because of this. And possible worlds are homomorphism of the Boolean algebra into 0, 1 because of this. You remember this. So I hope this was not entering a straight leg that could fracture your leg or your brain. When mathematicians give abrupt definitions and theorems without preparation, they sometimes cause the abandonment of students. So students that may have a gift for mathematical reasoning or a gift for mathematical or philosophy of mathematics are immediately thrown out. And some people, racists, say that mathematician is a special anthropological kind of man or woman. It's not a matter of anthropology. It's not a matter of anthropology. And then a fundamental definition, quantitative, non-explosive, very easily generalizable. What else? Definition of inconsistency. A book, so book is a map from finitely many events into the unit interval. Book is inconsistent if petty, the better. So we would say there exists a choice of stakes that ruin the better, the bookie. In which sense that this technical sum, which also might appear as breaking your legs, but this sum is smaller than 0. That means that Betty, by choosing to sell or buy the tickets in the lottery of Bookie, can ruin A. And then we introduce the crucial notion if you want to do probability. I never mention probability. I always put it between quotes because I don't want to define probability. Definitely was right. Probability doesn't exist. It should not be taught in elementary school because it's better not to teach it if it is taught in a bad way. That was definitely. A state is what should be, but it's a definition here. It is a map from the Boolean algebra into the unity interval that is additive on disjunction of incompatibles, of incompatible events. So there is probability here, but it is in a definition. And a definition, and then I insist that a state automatically with a three-line proof turn out to be monotonic. And then I gave sophisticated slides stating that homomorphisms are extremal states, and states, now I say that, I didn't say it yesterday, states are convex combinations of homomorphism. So there is a fraternity between homomorphisms, which are easy to see for anybody who has studied the minimum of algebra, and states. States are mixtures of homomorphism. Or if you prefer, homomorphism are extremal states in the convex space of state. Extremal states, so states that cannot be expressed by other states, except by saying this state is itself. It is not a combination of two states, convex combination. But the relation between states and the truth valuation is deep and it is fundamental. And then we met a proportion, analogy between analogies, and the man who said that if you are able to make analogy between analogies, well, that witnesses your gift as a mathematician. Because mathematicians in general are able to only to make analogies. But we must make analogies between analogies. Wonderful statement. Finally, the theorem, one of the glories of definity. The following conditions are equivalent for a book. The book ruins the lottery owner, bookie, in the sense that Betty can choose stakes, how to sell, how to buy the tickets in such a way that this famous sum is less than zero. So in any possible word, bookie loses money, which could be zillions, or extendability of the book to a state, something global on the whole Boolean algebra, an extendability characterization of consistency or inconsistency. So inconsistency is the non-extendability. Consistency is the extendability, which in logic is the familiar law. If and only if you can extend a truth valuation to a truth valuation of the whole algebra, you are consistent. You see, we recover logic as a fragment of this powerful definition for probability. Here is the analogy. This is an analogy between if and only ifs. So it's a rather sophisticated analogy. Application 1 was about independence with this theorem. Product is not in the definition of stochastically independent events. Product is rather the only possible operation to preserve consistency for any books which are independent in the logical sense, which is the good sense, the elementary sense. So the definition given by the product law follows again, as the other for incompatible, follows from this consistency theorem. It is not a minor achievement, but you remember Hilbert was sort of complaining that probability in 1905 had a mixture of definitions and axioms and blah, 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 which makes some confusion. 1905, definitely 1932, 17 years later. And then I did stretch a leg in an unfair way, saying that we are not doing finite probability. We are not doing Bayesian probability. We are not doing subjective probability. All the names by which these theories are sometimes classified by people who like to classify. This is probability theory. Probability doesn't exist. This is new. Oh, did I say that I finished? I'm so sorry. No, it's not it. The end was before, and this is new. This is new, just to let you remind that Kolmogorov built on probability a wonderful edifice and wrote that this axiom, this countable axiom, is gratuitous. He explained that this crucial axiom has no motivation, except that it explains many theories, many facts in mathematical probability theory. He was extremely honest. Definitely had an attitude completely different. He said, there is no countable additive probability. There is only finitely additive probability, if you wish, but there is this betting, selling, buying game. So the attitudes are extremely different. But the stone Karateodori conciliates this opposite views, as mathematics does sometimes. Opposite views, ideological wars, finite probability, infinite probability, are reconciled by a deep representation theorem. The fighters did not know the theorem, so they started fighting and blaming each other. But the theorem says, look, a state is a measure by an affine polynomial. It's the same thing, if you wish. Well, morality in mathematics. So, end of the summary plus this picture. I gave the first application about independence. Now I give you another application. I will give you three main applications of definitist ideas. The second application is that his theorem, his consistency theorem, gives a measure of the dependence of the truth value of a new event with respect to the truth values of the other events. You remember Boole. The object of probability is, given the probability, sorry to be so didactic, yeah? I'm sorry. Given the probability P1, Pn for events E1, UN, Pn, given En, given a new event, En plus 1, what are the possible probabilities Pn plus 1 for this new event? The object of probability according to Boole. The question is, if I modify, let's say, Pn, what happens to Pn plus 1? It's an extremely interesting question, because you have given the probability, but suppose you don't believe in the first one or in the last one, and you want to modify it. What happens to Pn plus 1? So if you modify one probability in the backlog of events that you have, what happens to the new event you wanted to investigate in the light of the old events? This is what I'm giving you as a second application of definitive theorem. So the usual situation, as we have elements of a Boolean algebra, so now we are mathematical, rigorous, with probabilities. Boole asked to determine the new probability of a new event. Definitely solve Boolean problem by stating that the new probability covers some interval in the unit interval. So it is connected, could be empty, in which case the probabilities are inconsistent. Now, suppose the probability of the last event, Pk, for the last event, Ak, undergoes a small perturbation. So you add an infinitesimal dpa, dpk. Infinitesimals may disturb you. I know. They disturbed Leibniz, they disturbed Newton, they disturbed many thinkers in the 16th, 17th, 18th century. I would say Dedekind made precise notions, but many brilliant mathematicians were able to work with these infinitesimals. okay? So we must be patient. If you never studied differential derivative, never mind. And think of dp as a small modification of the probability of an event. So suppose the probability of a last event, pk, 0.7. It was given 0.7. Suppose it undergoes a small modification, 1 million, plus 1 million. Then what happens to the probability of the new event, pk plus 1? Suppose it explodes. Well, by continuity, it will not happen, but it might change rapidly, even if you change the probability of pk by 1 million, in which case the k plus 1 event, the last event, depends tremendously on the k event. If otherwise, by modifying the probability pk a little bit, nothing happens to pk plus 1, the new probability, it means the new event does not depend essentially on the event, ak. So you see, we are measuring the dependence of the probability of a new event, as in Boole, the new event, not only what it can be, but how it is modified by perturbing, modifying only a little. Perturbation means modify by 1 million. Perturbation theory is small modification. You have to compute derivatives, but never mind, you modify by 1 millionth the probability. What happens to the probability of the new event? This is the problem. There are, and they were quoted in some talks, for instance by Walter, Sherlock Holmes was quoted about conflicting evidence and blah, 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 and I think because it's deeply related to the handling of uncertainty. So let's take from a crime case, you may copy it or formalize or take a picture. Either Peter or Paul, we are not to solve this problem. It's very difficult, by the way, but we have to understand this modification theory of probabilities. Somebody has been killed, and either Peter or Paul or Jane killed John because they were only people in the island when John died. He did not kill himself. He had a knife in his stomach, another knife in his rectum. If Jane is the killer, then either Peter or Paul or both help her because Jane is blind and cannot walk. There must be been at least 2 killers. These are the data Sherlock Holmes has. If you read Sherlock Holmes, you have always situations like this. What are, and here is Boole, Boole plus Sherlock Holmes. What are the possible truth values? Because here we are in logic. The possible truth values of the new event, Paul killed John. The possible truth values of that fourth event. Well, this is also Boole. The object of logic is given the truth values of event E1, and find the possible truth values of a new event. Here we have the situation, typically Boolean. Now look at the last statement. There must have been at least 2 killers. And look at the piece of evidence again. Yes, look at it. Sherlock Holmes' doubt on the third statements. There have been at least 2 killers. His informants about this event are not as reliable as his other informants. So he doubts a little bit about this and asks, how the probability of the event Paul killed John, which I wanted to know, depends on perturbing the probability of there must have been at least 2 killers. So you have evidence, but you doubt about a piece of evidence. And you say, if I modify the probability of this, the truth value of this, what happens? What is a modification of a truth value? There are only 2 truth values, 0 and 1 in this course. How do you mean to modify? And here, I would like you to be absolutely attentive. Truth values cannot be modified because there is a distance of 1 kilometer from 0 and 1. If I modify this 1 for the third event, I should go to 0. But now we have definitive for probabilities, which are in the full interval. What about modifying this one to 1 minus epsilon? Is it probability? Is it logic? A typical situation that explains the tangent of the parabola, for instance, and explains so many things in mathematics by perturbing outside the reality. They said, how can a line be determined by two coinciding points? Typical question. The tangent is a line which is determined by 2 points, as any line, but the 2 points are coinciding. Paradox. But if you do a lot of calculus, then you see that these 2 points are very infinitely linear, and for any blah, 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 there is a tangent, which is a secant, and in the limit you get a tangent. Here we are modifying truth values, thinking of them as probabilities. They are so near to 1 that it is a truth value plus a small modification. Remember definitive theorem. The possible new probabilities are covered a sub-interval of 0, 1. Okay, here is the basic intuition with the girl meditates. If t, say 1, is a truth value, then t minus dt, suppose dt is negative, okay? You decrease it by 1 million. This is something new for you, for everybody here at CU. I am modifying truth value by decreasing it by 1 million. How stupid. Wait a minute. We have a powerful theorem for the unity. Perturbed by an infinitesimal, 1 million, dt is still a truth value, which also obeys the definitive theorem for probabilities. You see, exactly by analogy with the, what is the tangent? The tangent is the limit of seconds when the 2 points, giving the secant, coincide. But there is no line for only 1 point. But there is for a parabola, for the circle. Here we are modifying a truth value, considering it as a truth value and simultaneously a probability. And we see what happens with definitive theorem. Isn't it beautiful? It's absurd because we are changing terminology. When truth values are infinitesimal close to 0, 1, they may be identified with probability values. And the full force of definitive consistency theorem, which is for probability, can be applied. We then have theorem. It's not entering, it's just a theorem which gives you, then the second application will finish. So patiently see what was proved in this paper. It was 1, okay? Or the maximum possible value of the event E4 varies continuously. This is the first important thing. Small modification, small variations, proving the continuity of the variation with the perturbed value 1 minus epsilon of the probability of the third event. You wanted to know the fourth event, how it varies if you change the probability of the third one continuously. This is the first very relaxing observation. Second, the derivative, the ratio between how it changes divided by how you change it, df on the epsilon. For those of you who have seen a derivative, it's such an important thing that if you have never seen, never mind. We have the limit of this change exists. And the quantity, of course, how this the new event depends on the previous event measures the degree of independence of the new event on the previous event. You see, we can measure how a new event depends on an old event if we modify the truth value of the old event. What happens to the new event? Of course, the highest is the derivative, the change. See, I didn't understand anything. Did anybody understand?
Can I have the name of the paper?
The differential in Boolean logic, something like that. A beautiful title to Epatele Bourgeois, okay? The differential in Boolean logic, which Boolean logic doesn't have differential. But it's in the annals, so evidently the referee was Epatele Bourgeois.
a small question, because I understand, I get the intuition, but like, don't you have to presuppose that it's differentiable, like they are not discrete? Isn't this a problem to be considered?
Differentiability problem.
Yeah.
You see, you have all this probability P1, Pn. So you put yourself, let's say, in the K cube. You have a K-dimensional space. I will not be technical, but I try to understand this. When you modify pk, you just modify one direction, the K direction. So it's a directional derivative. Luckily, because we will see that the logic that we study later has directional derivative and doesn't have differential in your sense. So the sheaves of Fernando, taking quotient by prime Elliot, now I am a bit technical, are exactly computing this direction. I will do that because it's beautiful geometry. I'm sure it will fascinate you. As I suppose it's fascinating you, the fact that derivatives exist and measures how the new event depends on the old event. Okay? In the probability language, but we are doing logic. It's fantastic. Well, it surprised me.
Thanks.
Please.
No, I said thanks.
De nada. It is always a rational number. Oh, it's an integer. No, usually it's not an integer. The dependence of the new event on the last event is a rational, but it's not an integer in general. Here is an example. It can be explained. Abscissa, the possible abscissa, the probability of the new event, En plus 1. The minimum and the maximum of the probability as given by definitive. For any fixed probability of the event Pn, not Pn plus 1, sorry, you have an interval for the probability of En plus 1. And here is the continuous behavior of the maximum and the minimum, so the interval, which is always an interval, continuously changing. For instance, at the beginning, you see that the derivative is quite strong. There is strong dependence of the new event on the old event. Then it stabilizes, the interval remains the same, and when you give 0.6 to the nth event, not to the n plus 1, error, I will use this here, write Pn, sorry. I'm changing my lectures, as I told, in the light of Fernando's course, and I make errors, and you are to correct me. Okay? So you see, at the beginning, it depends strongly. Then it stabilizes. Then it depends strongly again. Depends on the probability of the n event. What is the probability on the n plus 1? And you have derivatives here. Derivative in Boolean logic. End of application 2. So if you are a bit, as you say, frightened by derivatives, here there are derivatives essentially. Now we go to application 3. That definitive characterization of inconsistency allows us to measure how inconsistent how much inconsistency we are. Measuring the degree of inconsistency. We are in Boolean logic, embedded in probability. Okay, this can be generalized, and you will certainly generalize it to paraconsistency. But now we are doing it as an exercise to Boolean logic. And the question is, how much definitive characterization of inconsistency helps us to measure how inconsistent a set of premises are quantitative. You are tremendously inconsistent. You are moderately inconsistent everyday life. Those of us who are married, for instance, know about the degree of inconsistency or degree of those who have children. And those of you who have friends know that one can be very much inconsistent or very little inconsistent. What does it mean? Again, in Boolean logic, we can understand it. Let's see how. So we are giving a recipe to measure the degree of inconsistency, how much inconsistent is statement. So we meet this couple of fiancés, boyfriend and girlfriend, and yes, we relax a bit after derivatives, we should relax a little bit. But no more differential calculus. What is directional derivative? So one dimension. So R and Bill, Charles, Damien, and the butler shoot, and Peter is there. Another crime case, because there are nice cases to experiment our intuition, because Sherlock Holmes liked to express his mind on crime cases rather than, I don't know, mathematics. You see, crime case, somebody has been killed. Now, what is the situation? That's I should kill Peter. And here is the conflicting, as Walter would say, pieces of evidence. You don't need to read them. But you see, they tend to, so to say, tend to convince the inspector that the butler killed Peter. But Sherlock, again, and this is very important because this example will lead us to the main logic of this course, okay? There will be two logic in this course. Boolean logic, propositional. Children's logic, the logic which has so many mysteries anyway, it's so deep, and we have not finished to explore it. And then the other logic, which stands to Boolean logic as the two-element set of truth value of Boolean logic, stands to the interval. But isn't that probability? No, it's a logic. Logic of probability, I didn't say that. So Sherlock, with these pieces of evidence, which you don't need to read, but I tell you that point against the butler, doubts about this, and how many are 3, 6, this 8, I can't count. You know, Rota, the great mathematician, said, this is good for you to bring home. Mathematicians are divided into 3 classes. Those who can count and those who cannot count.
In general, they cannot count.
So we have 9 pieces of evidence, and Sherlock Holmes doubt about the bunch of pieces of evidence and says, if I drop 1, will the butler still be the favorite killer? If I drop 2, how much can I drop arbitrarily from this so that the butler still is the killer? See, there is logic minus premises. The more premises you can arbitrarily delete so that the same conclusion holds, the less reliable is this bunch of evidence. You see? For instance, if you cannot delete anything from this, if you delete one thing, then the butler is no longer, then you doubt. Because this is sensible to one premises. I don't know which one. And here is a fundamental problem of mathematics, by the way. So again, Sherlock doubts about these conflicting pieces of information and asks himself, if I arbitrarily delete one piece, does it still follow that the butler is the killer? No. And if I drop 2, does it still? And if I drop 5, see? Here is the problem in rigorous terms. We are given a set of pieces of information, Boolean formulas, for a criminal case, to fix ideas. Suppose these pieces of evidence yield a certain conclusion, psi, the butler is the killer. But we don't trust the overall information of big phi. We don't trust too much information, especially in these times, okay? Too much information. And wonder if by deleting 1 or 2 or E, I don't know how many, the same conclusion still holds. So the conclusion is stable under deletion of premises. And the theorem with Claudia Picardi is that this problem can be immediately reformulated, translatable. There is a quadratic time reduction for computer scientists. There is a translation for translation scholars. It is the consistency problems in the non-classical logic that will be studied throughout the rest of it. So, with this Sherlock Holmes innocent, there is the butler, this innocent problem we introduce to error correcting deduction. How much premises can I cancel that the conclusion is stable under cancellation? You understand? If I cannot cancel anything, the conclusion is extremely unstable. If I can, no, well, anyway, this is the problem. So we must fare la conoscenza, we must get acquainted with this new logic, which is in real life as odding bets by bookmakers are in the internet. So this logic that you will meet, an old logic, 100 years, but is as rooted in real life as Boolean logic. How will I present this logic? That was written in the title, Many-Valued Logic, but there were, Ariel gave many-valued logics, and other people gave many-valued logic. This will be one many-valued logic, different from Boolean logic, many-valued, certainly. And so I have to introduce one logic. Let's see how one logic can be introduced. We are motivated by Sherlock Holmes' tolerance, E-fault tolerance in real life. Because logic, if you think of Boole wanted to understand the brain, think. And Boolean logic is a gift to mankind by Boole. Now, I suppose Marcelo fingers, oh, now we have a satellite, a receiver, distortion, noise. This will be ending quickly. I'm not waiving computer science or correcting codes or transmission channels. So be patient. But it is useful because the logic stems out from this sort of transmission with errors, exactly as Sherlock Holmes' problem depended on errors in a set of evidence. You may consider it as a straight leg, but you see that it is a beautiful game. It's refreshing and entertaining. So the situation is a transmitter by a satellite, which is weak, and receiver is a powerful receiving station, but there is between satellite and station noise, distortion. The satellite sends information through a noisy, it's called channel, even if there is no water. There is nothing, in fact. There is distortion. Up to E, the number of errors in the Sherlock Holmes program. So we know that up to 7 bits may be erroneous. So this is an important data. Sherlock Holmes asked if by cancelling 3 pieces of information, the conclusion still holds true. Here we are asking, those who know will call it error correcting code with E errors, so it's something well established. Up to E bits are distorted, may be distorted during a transmission. So what do people know, mankind? Well, instead of sending the minimum number of bits, they add redundancies. I will insist on redundancy. This is an example of the Berlekamp-Dobrushin theory of communication with feedback. Because the receiver tells the satellite, what did you send me? What did you send me? Feedback. To simplify matters. It is a chapter of error correcting codes. Where is the logic? Where is Sherlock Holmes? Where is it? It is here. There is a girl and a boy who answers questions. The boy sends bits to the girl. The bits of a number, of a secret number that the boy has in his head, and the girl wants to know. This is the famous game, Think of a Number. Each country has the translation of this game. Pensa un numero, think of a number in Italian, and in Brazil they certainly have this. Usually it's not with numbers, but with people. Try to guess this person by the question. Here we do it with numbers. What is your bit? 1. So the boy sends bit 1, but there is distortion. And the girl says, perhaps it was 0. Okay, what is it? From the receiver's viewpoint, satellite station, it is immaterial whether the wrong bits are due to distortion, so honest distortion, or errors in the transmission, or ignorance, or lies. We are doing a treatment of lies, error, distortion, ignorance. In any case, the problem is to minimize the length of the transmission. In this two-way communication, the worst, suppose there is E errors, say 3 errors. Then one way is to ask 2E plus 1 questions for each time. This is a lemma, it's so easy. Suppose there is 1 error. Suppose there is 1 error. If you ask 3 times each question, then you are safe, because the guy can reply yes, no, no. And you see which has the majority of the answers, and that is the correct answer. There is a famous quotation by Lewis Carroll. What I tell you 3 times is true. This is the bad way of correct information when there is 1 error. Ask 3 times each question about the bit, and then take the majority of answers. But what mankind has invented as much more efficient ways of interacting under distortion, which is not what will interest us. What will interest us is the logic of this game. So classical error correcting codes, all the bits are sent at the beginning and there is no feedback from the receiver. The worst possible situation is when you go back and forth many times, but this is not interest of us. There is this which may interest you, that mathematics must be open. That is with a question mark, because I may be betraying Fernando after I will ask him. Mathematics must be open to suggestions coming from real life problems and revolutions. This is very important. You must have sensitive ears for such things. Analysis and thermodynamics were deeply motivated and had a tremendous development because mankind, some part of mankind, wanted to dominate energy. Computer science, artificial intelligence, what some people will do here in their course, had a tremendous impact now in mathematics because some people, want to dominate information. So these are the magic words: energy, calculus; information, computer science, and so on. Here we have a modest fraction of knowledge, which is correcting codes. How to cope with wrong information, Sherlock Holmes and a transmitter. We are not interested in optimization, because this is not a course in engineering, but we are interested in the logic of the underlying game. And the logic has 2 fathers, 2 important fathers. One is Stanislaw Ulam, who wrote the following in his Adventures. Okay, let me read this quotation so you see that what we are doing is rooted in mathematical culture. Ulam was a great mathematician from the Lviv school. He emigrated in Los Alamos. Rota met him. There are pictures of the two. But of the many things he did, I would like to stress that someone thinks of a number between 1 and 1 million, which is just less than 2 to the 20. Here you see the engineer, Los Alamos. Another person is allowed to ask up to 20 questions, to each of which the first person is supposed to answer only yes or no. 20 question game. 2 to the 20 is 2 to the 10 square. 2 to the 10 is 1,000 square, 1 million. No, 2 to the 10 is not 1,000. it is somewhat more than 1,000. So 2 to the 20.
1056.
Yeah. So 2 to the 20 should suffice because you have. Now let's see. Obviously, the number can be guessed by asking first, is the number in the first million? And then again reduce the reservoir of numbers in the next question by 1/2. Is the number in the first $500,000, blah, blah, and so on. Finally, the number is obtained in less than logarithm of 2, 20, about 20. Now suppose one were allowed to lie once or twice in the answers. It's a wonderful, but by intelligent. If there are lies or distortion, but here it's beautiful to dramatize with lies. Lies is more important than distortion for us logicians. Suppose you are allowed once or twice, then how many questions would one need to get the right answer? One clearly needs more than 20 questions for guessing the 2 to the n. Now it generalizes. One clearly needs more than n question to guessing one of the 2 to the n. Okay, it's generalizing from 2 to the 20 to 2 to the n. Needs more if there are lies, because you can repeat the question and 2n plus 1 times. Yeah. This problem is not solved. It was not solved in general. It was just behind there, so not solved in general. Come on. And Alfred Rényi, another great probabilist, says the same. Let me read it for you so that you can see the analogy between the problem. So the problem has double motivation. I made up the following version, which I call the Bar Kochba with lies. Assume that the number of questions which can be asked to figure out the something, your number, your secret number, is fixed. And one who answers is allowed to lie a certain number of times. Ulam said 1 or 2, here said a certain number of times. The questioner, of course, doesn't know which answer is true and which is not. Moreover, the one answering is not required to lie as many times as is allowed. So less or equal E lies. For instance, you know, it does seem a very, so if 2 or more lies are allowed, then the calculation of the minimum number is quite complicated. It seems to be a very profound problem. So when Ulam and Rényi tells you that this 20 question game with lies is a very profound problem, we must rely, we must trust them. The 20 question game with no lies is familiar to all of you who have played the game. Think of this person. Is he married? No. Does he live here? No. Is he tall? No. Is he stupid? Yes. And so on, and little by little, well, stupid, you try to ask interesting questions that can, how to say, half the search page each time. Otherwise, you go on, can you tell me the initial? No. The questions are yes-no questions. So guess my number, X, the secret number, in 1, 2, 3, blah, 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 8. And the girl, is it odd? She read Ulam. Is it odd? With no lies, it's like that. But I want to stress the underlying logic of the game without lies, so that you then appreciate what happens to the game with lies, because this is error correction, and this is the logic I would like to introduce today. Is it odd? Yes. Observe. Before the question, all numbers 1 to 8 have truth value 1, in the sense that are they still possible numbers? Yes, all of them, they are in the search space. All of them 8 are truth value 1, in the sense that they have not been cancelled from the search. And if the boy answers, or the girl, but I forgot who is playing with. Yes, if the girl answers yes, it is odd. What happens in Boolean logic? This is a Boolean function, by the way. A Boolean function is a function that has value over the search space 0 or 1. And if the number is odd, 1, 3, 5, and 7, maintain the truth value 1. I'm sorry to be so detailed, but when I'm doing it with one lie, you will be prepared. Okay, so forgive me, read your newspaper, take your phone now, because the game without lies is easy. And what happens to 2, 4, 6, 8? They do not confirm with the answer, so they are discarded from the search space. And the search space is now shorter. It has been halved. Is it odd? No. Then the answer would be this, okay? The odd numbers would disappear and the even numbers would resist in the search space. Again, without lies, I will give you the 4 questions which are, this is the initial state of knowledge. Is it odd? No. Is it bigger or equal 6? Yes. What happened? With respect to what you knew, that the even numbers were still in game, bigger or equal 6, so only 6 and 8 resist in the search space. Is it clear? Yeah? Because I'm going now far. Is it 8? There are 2 numbers. Is it 8? No. Then it is 6. And the game finishes. Children mathematics, okay? But children mathematics, they become high school mathematics, university research mathematics quickly, with one lie already. Note, we are taking Boolean conjunctions of the answers. So Boolean logic dominates the game without lies. And now, with one lie. Okay, so be ready here. Take note. It's very simple. Is it odd? No, guess my number x in 1, 8. Is it odd? Of course, Pinocchio nose doesn't get longer when he lies. So this is a game with a liar, but his nose does not get longer. Otherwise, it is without lies. Because if his nose goes bigger, then it takes the opposite answer. Okay, that's clear. So this is a stable Pinocchio nose game with one lie. Is it odd? The effect of this answer, yes. What happens to the odd numbers? They still have truth value 1. What happens to the even numbers? You cannot discard them because there could be a lie. So you put them in the purgatorium or in the limbus of those numbers which could be affected by one lie. The truth value 1/2 appears in the most natural way for numbers that are still in the game, but with a criminal record worse than the other numbers. Those are 1 in the search, and these are 1/2. They are still good. You see, a number has truth value 1/2 because it's still in the game, but one lie has been told on him. So he has a sort of, I don't know, something in his criminal record. We go on. Is it odd? No. You do the same. Even numbers, truth value 1. Odd numbers, truth value 1/2. And let's play a game. With 4 questions will not suffice. As Ulam said, let's verify that 4 questions will not suffice. So initially, all numbers have truth value 1. Is it odd? No. So odd numbers get truth value 1/2. Is it bigger or equal 6? Yes. What happens? Bigger or equal 6 remain with their truth values, even the criminal number, and the other are eliminated. Is it 8? No, but there is 2 numbers still. So play the game and you verify this. We are taking Łukasiewicz conjunction of the answers, just as before we were taking Boole conjunction of the answer. A third truth value appears because there is one lie, and very natural, the handling of our knowledge during the game is coded by Łukasiewicz functions with 3 values. Okay? On the search space with 8 elements, 3 questions suffice if there are no lies, but do not suffice if there is one lie. 2-lie game, be patient, but then I will never play this game anymore. Is it odd? Yes. Now, numbers, the odd numbers keep their truth value. They are pure, immaculate, honest, with a wonderful criminal record. And the even numbers, you cannot discard them to value 0. You cannot give 1/2 because there are now 2 possibilities. You give them 2/3 to show that they are still with they still in the game, but one lie was told to them. Let's go on. No is the same thing dually. Let's play it again for proof. Is it odd? No. Observe there are 4 truth values. We are doing Łukasiewicz 4 values. Don't worry. Is it bigger equal 6? Then this is the situation. Is it 8? No. And this is the complicated situation. All numbers are still in the game. 2 lies are much worse than 1 lie. We are taking Łukasiewicz conjunctions of the answers. Methodological remark. Again, Fernando, forgive me if I'm betraying you. Łukasiewicz did not invent his operation as a tool to handle mendacious answers in Ulam gaming. Łukasiewicz was 1920, Reini and Ulam the 40s and 50s. Similarly, and much more importantly, the ellipsis was contemplated by mankind for over 20 centuries or 19 before it was found stably working in the sky by Kepler's law. So something may resist in mathematics for 19 centuries, and then you happen to discover it in your house, in the sky, your brother. This is another important thing. If I'm wrong, forgive me, because students must be against their teacher. So you're right also in this, okay? So inconsistency in this game. This is our main point now to understand inconsistency. Oh yeah. Shout, please.
Okay, just to clarify, it doesn't matter whether the lie is obligatory or voluntary, right?
From the viewpoint of search, doesn't matter, and it need not even lie, as you remember, Ulam, at most 1 lie or 2, if he wishes to lie. In fact, the satellite doesn't know how many of its bits will be distorted. We conjecture by a probabilistic, whatever it means, computation that E of them, we know how many bits it should send, say 1 zillion. There is a probability, blah, 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 and so we conjecture that 25 bits could be wrong. At most 25. That's what I'm doing in error correcting code. Here the game is the same. They fix a number of lies. Of course, if you want to deal with the current life, you should put infinitely many lies. But with infinitely many lies, you couldn't find the secret number. Observe this. You take a picture of this. 2 opposite answers to the same repeated question do not lead to the explosion of the game. The game goes on. The show goes on. The game must go on. Pinocchio, is it odd? Yes. Is it odd? No. Normal. Inconsistency doesn't kill the game if there is at least 1 lie. In the Boolean game, where there are lies, no number remains, so there is no number. But here we are working with lies, errors, disturbance. In this sense, the game is also inconsistency tolerant. And here we have a father, an old father, with hair, by the way. It's not Hilbert, this is Aristotle. So tertium non datur failed here. Give me more about this logic. I like it. He liked the Stoic logic, he liked many logic. No, he didn't know about this. He likes it. And we answer to Aristotle in this as a homage. In the beginning, there was only 1 truth value, true. In fact, there was the chaos, but the chaos was true. And with entropy, probably we're going to chaos again. But anyway, in the beginning, there was only truth. Then the Greeks invented a second truth value. It was one of the greatest inventions in mathematics. A second truth value. There was truth, they invented plain falsity, falsum. And using this new truth value, they proved, for instance, the infinity of primes, with the same proof that today we teach in the junior school, in the high school. Reasoning by absurdum, so using this new truth value, they were able to prove fundamental theorems in mathematics, proved by reduction ad absurdum. Two truth values. And then for the Ulam game, it turns out that you need more, because some numbers could be there with a criminal record, but not yet thrown out from the search space. We have, look at the game with two lies, numbers with 4 truth values. Let me briefly recapitulate the richness of the game. Question is a subset of the search space. Now I want to give precise definition because this is mathematics. The question is the number odd? Means you present the set of odd numbers. Answer, 0 or 1, with the meaning that up to E answers can be false, wrong, distorted. Incompatible state, all candidates have been killed. Initial state, all candidates are there with their pureness, with their criminal record, full. 1, true, I'm there. Order, state of knowledge is more informative than another state of knowledge. You aim to get a state of knowledge which leaves only one number alive. And you do it by increasing the information of the state. Physically, it is the functions go down and down and down until one number survives with non-zero truth value. This is the solution of the game. Positive or negative effect of an answer, you have seen it before. In the case of 0, 1, and 2 lies. State of knowledge, the Łukasiewicz conjunction, and here comes the Łukasiewicz conjunction as well, of the effects of the answers. Your knowledge in the game with lies is given by Łukasiewicz conjunction of the answers. So much for Łukasiewicz conjunction. You remember, Boole deduction was not defined as today we know it. It was a Boole disjunction. It was a partial operation. It had to undergo an extension by various people. Łukasiewicz conjunction was born like this. No one knows why. Well, in fact, he wanted to prove something about Aristotle, but the conjunction holds in the Ulam game for all numbers. For the game with no lies, the following defining equation of Boolean algebras provide, via equational logic, substitution of equals by equal, all equations satisfied in the game with no lies. In other words, I'm giving you the axiomatization of Boolean algebras, which you know, but I give you a cute axiomatization with a minimum, not the minimum, not the absolute minimum, but the minimum that serves us to speak of Łukasiewicz logic. Okay? Here they are. They are 7, 8, well, count them, I can't count. And there is the last one, which says that x and x is equal to x. Repetita iuban. Repeating a formula doesn't give new information in Boolean logic. It's terrible, isn't it? But Boolean logic has this idempotence rule, x and x is x. Let me use the O dot symbol instead of conjunction. This conjunction we call, or the ampersand, because I want to generalize Łukasiewicz. Okay? In the game with lies, not all equations of Boolean logic holds. So the game with lies has special properties. Let's see. The idempotence law, x and x is the same as X generally pays. Think of this guy who is phoning under a thunderstorm, and they give him the bit. Can you repeat? I didn't assume when. You see, redundancy occurs when there is distortion. When there are lies, you need to ask more times. So let's return on this. It is not true when there are lies that S and S is equal to S. S and S is more informative than S. So we are introducing, Łukasiewicz knew well, a logic where idempotence fails. Very good. Okay? So the fact that there are lies destroys idempotence. X and X different from X. Is it odd? Yes. Is it odd? Yes. It gives more information if there are lies. Repetita iuvant. Repetitions are useful. The Romans had this proverb, and Łukasiewicz incorporates this beautiful fact in his logic. Two equal answers to the same repeated question give more information than a single answer on that question. The Boolean idempotency law fails for the conjunctions of answers in Łukasiewicz's game with lies. Then we have to handle a game with less equations probably, or with new equations that are special with lies, who knows? And then you will have a surprise. The conjunction of the states is given by Łukasiewicz conjunction of the answers. When there are no lies, this is Boolean conjunction. We have seen that S and S is not equivalent to S. Which equation hold true in the game? For instance, now I give you equation that holds associativity. X and Y and Z is the same information as X and Y and Z. Associativity holds. Try it again and you will see that. However you regroup the answers, the information is the same. You can verify it on the ground by playing the game if you wish, or trust me. If one is the initial state where all numbers are pure with wonderful record, criminal record, then you have an answer, say A, then A, and this state is A because it's no information. They are very good names. If 0 denotes the state where all numbers are dead, A and 0 is 0. More information, they were dead, they are dead. You can resuscitate in with not X, and there is a difficulty here to compute. It's an exercise for which the meditating girl will help you if you wish to do the exercise. You have that not X equal X. Yes, because 1 minus X is equal to X. So, okay. But more difficult equation, please verify it if you like to be introduced in Ulangue. These games are very useful. X and not Y and not X is the minimum, so it commutes. This is I read difficult, but for you it should be easy. You can verify it. I will not prove it. And now, C, shout.
What does associativity mean exactly? Like, does it mean asking once A or A and B, then asking C?
You have the answers. You write down on the tables. You can regroup them. I received A and B, okay, and then I received C. Or perhaps I received B and C and A, because all the, and however you regroup the answers, the effect is the same.
But like you receive B and C means that you ask, like B and C?
Didn't understand.
Like you can ask stuff as like an expression, right? So you can ask like, is the number odd or is it even? Something like that.
Yes.
So you're saying that if I ask, for instance, is the number 2 and it is like, you know, like if I group stuff logically in the question.
S is a well-defined answer. T is a well-defined answer, R is a well-defined answer. You can write, you don't know yet that conjunction is associative, so you must, it's a binary operation, you must write them with a binary operation. Then you can write S and T and U, or S and T and U. The effect is the same, so you can drop parentheses. This is there, nothing else. Okay, tired. Fundamental question. Does there exist a set of equations from which, like in Boolean logic, all equations valid in any possible game with lies can be obtained by equational logic, so by substitution of equals by equals, nothing more. Equational logic is the logic that everyone learns when he is a child. For Boolean logic, this is the situation. From these, by substitution, you get everything which is true in the game with no lies or in Boolean algebra. And when there are E lies, what happens? We are posing nothing less the completeness problem for the logic of the game, Ulam-Reyni game with lies. So this innocent looking question is the posing a completeness problem. And as you know, completeness problem always are a damnation for logicians, because proving completeness is always difficult, it's non-trivial. You have to prove that, you have to give some equation and then show that everything follows from those. Well, the answer is surprising, okay? And the answer is yes. What we already projected or posted is all that is necessary and sufficient to derive everything in Ulam's game. This was proved by C.C. Chang, model theorist. So he did not this stuff in his life. He did something, but he was a model theorist. He did other things. But he proved the completeness theorem, algebraically speaking. The equation, by the way, Gödel in 1930 proved that the rules of deduction that we know since 2,500 years or more are complete. An achievement. Gödel's completeness theorem sanctioned, or how you say, sanctified the rules that were old by 15 centuries or 25 centuries. And here is the theorem by Chang. The following equations, and the question is, do you remember the Boolean equation? Can you compare with this? The following equations are all that you need to derive any equation valid in Ulam game with lies, with any number of lies. If there are no lies, you go to Boolean logic. And what is the difference? Well, the last axiom, x and x equal x, no longer appears. So they are simpler. They are simpler. We are generalizing Boolean logic in a simple way. Let's have a look. No lies, then repeating thing doesn't help. No lies. Lies, you don't have the axiom. Chang, these are the complete axioms for logic with lies. A wonderful theorem. 1959, 40 years after Łukasiewicz introduced this logic. Understand the difference? Yes. Repetita iuvant. I drop the idempotency equation. Okay, I think I will not now make precise the notion of logic, because I want to show that this logic is not arising only from a game, a beautiful game, Reyni Ulam, but I want to show you that, like Boolean logic, this logic is here to stay. It's here to stay. It is born from a game or from something else. There are many roots for this logic, but it's here to stay because it has uniqueness properties that will hopefully convince you of its beauty and sense and necessity in logic. Okay? okay? But I will do this tomorrow for those of you who patiently will follow.
Yeah, so we can derive commutativity from these laws, yes?
Beautiful question, of course. Thank you for your question. It's not me. Kolarczyk, which is not Jerzabek, okay? A few years ago, in the Czech Mathematical Journal or in some Tatra Mountain Journal, proved that commutativity follows from these three equations, 4, 7, 5, well, few, okay? Kolarczyk has this beautiful theorem, the commutativity axiom in Łukasiewicz infinite valued logic follows from the other axiom. Wonderful. In fact, so then I can write presentation. Shout, or somebody here for me, and then shout for me.
What is do you have any results on the complexity of this logic? And is the parameter a fixed parameter that can bound the complexity with respect to classical logic?
Thank you for this question. I prove, blah, blah, blah. Thanks for this question. I yes, it's my theorem. Well, Fernando, I'm quoting my theorem. I already quoted 5 or 6 times. Anyway, yes, it is NP complete, exactly like Boolean logic. Okay? It was theoretical computer science 65 years ago, 40 years ago.
Do we have representation theorem for these algebras?
Bang! You see how it means to pay people to ask the right question.
You are trying to escape, not to show your results, but people are asking you.
They ask because they don't know my result. I should try, yeah. Yes. What did you ask?
Representation.
Yeah.
So
I would say that's McNaughton anyway. It's not Mundici, it's McNaughton, 1951, Journal of Symbolic Logic, a wonderful representation theory for the free and the algebra. This was in a function director non-derivative exists, and so a fantastic theorem comparable in weight and effect to Chang's completeness theorem. Yes, yes, yes.
Yeah, so that's profound. I didn't quite get how you evaluate the formulas using the games.
Next years.
Let's see.
So, the game has a search space and 25 elements. And the initial state where everything has truth value. And the number of errors, say 1 to fix values. Then there are three truth values. 1, you are full honest, your record, criminal record is no crime. 1/2, 1 crime, in the sense that you may still be there, but Pinocchio has lied about you. 0, Pinocchio has lied too much on you, 2 or more times. And then what did you ask? What did you ask with this apparatus? I show you the answers and how
You said that the state of knowledge is the
Conjunction of the answers.
Łukasiewicz conjunction of the question or
Of the answers,
Yeah.
of the effects of the answers.
Yeah.
Yes or no? Yes.
so. How are the questions?
Questions are subsets. Is the number odd? Questions are subsets of the search space.
Okay. And the answers?
Yes or
The
no?
answer are yes or no. Yes kills a little bit those who are no. Kills not by eliminating them,
Oh,
by
literally like one,
well,
and
no,
one,
yeah,
and zero,
they
and
decrease by a little
Okay.
the false number. In Boolean logic, you decrease to death the number. Here, if there are 25, if there are 100 errors, you decrease by 1 divided 9.
so 1 and 1 and 1 and 0 would be some value in between.
Yes.
Okay.
Rodolfo.
Some recommendation. You said
Rodolfo,
It
now,
was proved-
please, everybody
it was
wants to
proved
hear.
recently. Collage, yes.
When is this?
I don't remember, but if you go in or Mathematica Bohemia or Data Mantor, or Czech Mathematical Journal in the last 5 years, you find. But if you look Collaric, you find it. And if you write to me, I will tell you the precise reference, of course.
Any more question?
Yeah, one. What's the relationship between derivatives and line?
Derivative and line. Too deep question, but I have an answer. I showed you the equations that hold in any game for any number of lines. This is the algebra of the logic. First question. So we are not entering into the proof theory, which is NP complete, but we are staying at the algebraic level because it helps a lot. To be brief, McNaughton, 1951, Journal of Symbolic Logic, proved that the free algebra, just as Boolean algebras are zero, Boolean function, as you know, 0 or 1 values, as in the zero lie game, the equivalence classes of formulas, so the elements of the free MV algebra, many-valued algebra, are piecewise linear. Oh, you know that. My God, why did you ask? You are piecewise are functions which are derivable along any direction. And you know that, and why should you ask? Well, you ask and I answer. The free MV algebra allows directional derivatives. Okay, that's the answer for the moment. I will speak about this with beautiful paintings.
Today it wasn't kind of put together.
Sure. You know everything and you ask this question. Peter was shocked. Marcelo was shocked. Please.
We know that the MV algebras are the same that BCK evolutive algebras, right? Yes. And you show the games to give us an interpretation of this. And we had another interpretation for similar cases, for example, BCW algebras.
You know, BCK algebras are based on subtraction. And the algebras are based on conjunction the answer, which is more natural. Yes, the number is odd, the number is bigger than 6. BCK algebras would require a beautiful game where subtraction is, I think it could be invented. Rather than subtraction, I would put double subtraction, symmetric difference, which could help for a game. But since I haven't found this subtraction-based game, I presented it with the conjunction-based game of Ulan game. I could try with Ulan game and subtraction, but it would be unnatural because the answers are put together by conjunction. Okay?
Thanks for the presentation. I have some doubt about the relation of this new logic and relation to information, precisely with the notion of reducing uncertainty in these games. These games, normally yes or no questions reduce uncertainty in the domain. You see a path for some kind of information logic information in the sense of reducing uncertainty in the system.
Or handling uncertainty in the system. Well, I would pray Marcelo, who does Łukasiewicz PSAT, to do something on this. This is computer science and artificial intelligence. I know that very logic has applications in artificial intelligence, exactly this problem and a related problem. I don't know if you talk about that, probably no.
Maybe tomorrow.
Maybe tomorrow. So maybe tomorrow, a guy who knows more than me. And thanks you, Marcelo, because
Well,
otherwise
I
it's...
wanted you to mention another result of yours that correlates Łukasiewicz with Maxa.
max up isn't the problem of Sherlock Holmes how much I can delete from my database to be consistent. That's max up. You see, I did it. I didn't say max up because I didn't want to terrorize computer scientists or other, but it is, I did it. I did it.
You can cite another result of yours.
Picardi, a girl, a professor of computer science in Turing. Ask a question. Thank you.
This might be a question of housekeeping. So is it, I mean, can this algebra be extended into such kind of relational algebra?
There must be someone who did answer your question in Salerno. I don't know this, so I don't know. But I'm sorry. It should be done, of course, as is done for Boolean algebra. The same. If you write to me exactly what would you like to see of relational algebra about after I've done MB anyway, which are the equations I gave, then I will try to address you to those people who do something related to your class. Okay?
Thank you.
Any more question? Rodolfo.
Can you say something regarding all the theoretic point of view here, just equations from the order point of view? I mean, this is not a real infinite. The addition, the multiplication defines a lattice order on MB algebras, and then a categorical equivalence shows that MB algebras are the same as lattice ordered abelian group with a strong unit. So you have only one possible. So you go into mainstream mathematics. Lattice ordered abelian group with strong unit.